MEG 224, Engineering Mechanics, Dynamics. Lecture 5, the concluding part of Lecture 5, Kinetics of Particles, the Principle of Impulse and Momentum, Part C. As earlier said, this lecture can be found in Chapter 15 of Engineering Mechanics, Dynamics by R.C. Hibler. Lecture objective. The objective for this Part C is to analyze the mechanics of impact. Impact occurs when two bodies collide with each other. Impact occurs when two bodies collide with each other during a very short period of time, causing relatively large impulsive forces to be exerted between the bodies. So, such as when there is a head-on collision in an accident. So, the striking of a hammer on a nail or a golf club on a ball are common examples of impact loadings. In general, there are two types of impact. Central impact occur when the direction of motion of the mass centers of the two colliding particles is along a line passing through the mass center of the particles. It can be seen here that the two object A is coming from the left towards the right on x-axis. Object B is coming from the right, going to the left on the x-axis. Their y component, the y component of their velocity is 0, and they collide. So that x-axis that passes through their center of mass is the line of impact, while the y-axis is the plane of contact. Then, when the motion of one or both of the particles make an angle with the line of impact, as shown here, the impact is said to be oblique. So the object is coming, object B could be coming from the left on the x-axis, and then A coming from an angle to hit it. Or the two of them can be coming from different angles. So central impact. So to illustrate the method for analyzing the mechanics of impact, consider the case involving the central impact of two particles A and B shown in the figures. So the particles have the initial momenta shown in figure A. So you know that the momentum is not, it has nothing to do with, it's not impact. Momentum is just mass times velocity. So object A is moving with velocity A, and the object B is moving with velocity B. And the object A is having a higher velocity than object B. So eventually, object A will overtake object B and crash into object B or collide with object B. So provided VA1 is greater than VB2, collision will eventually occur. During the collision, the particles must be thought to be as a deformable or non-rigid bodies. The particles will undergo a period of deformation such that they exert an equal but opposite deformation impulse, integral PDT, on each other. So action and reaction, they are equal and opposite. So as particle A or object A collides with object B, then object B will react in the opposite direction. So this line of force is effect of A on B, while the line of force here is the effect of B on A. So action and reaction equal and opposite. Only at the instant of maximum deformation will both particles move with a common velocity v, since their relative motion is 0. So they will now stick together. Since the velocity of B is higher than that of A, so they will move with a common velocity that is neither of VA nor VB. So afterwards, a period of restitution occurs, in which case the particles will either return to their original shape or remain permanently deformed. Each of them can return back, or either of them can return back, or both of them may be deformed. So the equal but opposite restitution impulse is integral r dt, which pushes the particles apart from one another, as shown here. So in reality, the physical properties of any two bodies are such that the deformation impulse will always be greater than that of restitution. So this is the deformation impulse. This is restitution impulse. If restitution impulse is greater than deformation impulse, it's not possible, because when there is impact, there will be noise, there will be heat, and all those things which are lost energy that can never be recovered. Just after separation, the particles will have the final momenta shown in figure E, where VB2 is greater than VBA. So this is the instance after the impact. The VA, the particle A, is still moving, particle B is moving ahead. So there will no longer be any collision again, because VB2 is greater than VA2. In most problems, the initial velocities of the particles will be known, and it will be necessary to determine their final velocity, VA2 and VB2. In this regard, momentum for the system of particles is conserved during collision. Is conserved, since during collision, the internal impulses of deformation and restitution cancels out. That is, impulse impulse deformation and impulse restitution, they are equal and opposite. Hence, referring to figure A and E, we require that MAVA1 plus MBVB1 is equal to MAVA2 and MBVB2. This is conservation of momentum, or linear conservation of momentum. In order to obtain a second equation necessary to solve for VA2 and VB2, we must apply the principle of impulse and momentum to each of the particles. For example, during the deformation phase of particle A, at this figure A, B, and C, we have that MAVA1 integral P dt is equal to MAV. For the restitution phase, which is illustrated in figures C, D, and E, MAV minus integral R dt equals MAVA2. So the ratio of the restitution impulse to the deformation impulse is called the coefficient of restitution. From the above equations, this value for particle A is E is equal to integral R dt over integral P dt. That is output over input. That's my own definition. which is equal to V minus VA2 over VA1 minus V, where V is their final velocity together. In a similar manner, we can establish E by considering particle B. This yields E is equal to integral R dt over integral P dt, which is equal to VB2 minus V over V minus VB1. If the unknown V is eliminated from the equation, from the two equations above, the coefficient of restitution can be expressed in terms of particles' initial and final velocities as VB2 minus VA2 over VA1 minus VB1. Provided a value for E is specified, the equation, those two equations, 10 and 11, can be solved simultaneously to obtain VA2 and VB2. In doing so, however, it is important to carefully establish a sign convention for defining the positive direction for both VA and VB, and then use it consistently when writing both equations. Else, there will be confusion, and then the details will be lost. As noted from the application shown and indicated symbolically by the arrow in parentheses, we have defined the positive direction to the right when referring to motion of both A and B. That is, positive X is positive. Consequently, if a negative value results from the solution of either VA2 or VB2, it indicates motion is to the left. Coefficient of restitution. From figures A and E, it is seen that equation 11 states that E is equal to the ratio of the relative velocity of the particles separation just after impact, that is VB2 minus VA, to the relative velocity of the particles approach just before impact, VA1 minus VB1. By measuring these relative velocities experimentally, it has been found that E varies appreciably with impact velocity as well as with the size and shape of the colliding bodies. For these reasons, the coefficient of restitution is reliable only when used with data which closely approximate the conditions which were known to exist when measurements of it were made. In general, E has a value between 0 and 1, and one should be aware of the physical meaning of these two limits. Elastic impact. If the collision between the two particles is perfectly elastic, the deformation impulse, integral P dt, is equal and opposite to the restitution impulse, integral R dt. Although in reality, this can never be achieved. E is equal to 1 for an elastic collision, plastic impact, where E is equal to 0. This impact is said to be inelastic or plastic when E is equal to 0. In this case, there is no restitution impulse at all, so that after the collision, both the particles couple or stick together and move with a common velocity V. From the above derivation, it should be evident that the principle of work and energy cannot be used for the analysis of impact problems, since it is not possible to know how the internal forces of deformation and restitution vary or displace during the collision. By knowing the particles' velocities before and after collision, however, the energy loss during collision can be calculated on the basis of the difference in the particles' kinetic energy. This energy loss, summation U from 1 to 2, is equal to summation T2 minus T1. That is the final kinetic energy minus the initial kinetic energy. That is, total energy loss is is equal to total final kinetic energy minus total initial kinetic energy, which occurs because some of the kinetic energy initially of the particle is transformed into thermal energy, as well as creating sand and localized deformation of the material when the collision occurs. In particular, if the impact is perfectly elastic, no energy will be lost in the collision. Whereas if the collision is plastic, the energy loss during collision will be maximum. Oblique impact. When oblique impact occurs between two smooth particles, the particles move away from each other with velocities having unknown directions as well as unknown magnitudes. Provided the initial velocities are known, then four unknowns are present in the problem. As shown in figure A, these unknowns may be represented either as VA2, VB2, then theta2 and phi2. That is the final velocity of particle A, final velocity of particle B, the angle of the velocity B, of the final velocity of particle A with line of impact, and the angle of the velocity of particle B with line of impact. If the y-axis is established within the plane of contact and the x-axis along the line of impact, the impulsive force of deformation and restitution act only in the x direction, as shown here. So by resolving the velocities or momentum vectors into components along the x and y axis in figure B, it's then possible to write four independent scalar equations in order to determine VAX2, VAY2, VBX2, and then VBY2. Momentum of the system is conserved along the line of impact, that is x-axis, so that summation MVX1 is equal to summation MVX2. The coefficient of restitution will now be VBX2 minus VAX2 over VAX1 minus VBX1, which relates the relative velocity components of the particles along the line of impact, that is along x-axis. If these two equations are solved simultaneously, we obtain VAX2 and then VBX2, that is the final velocity of particles A and B in the x direction. Momentum of particle A is conserved along the y-axis, perpendicular to the line of impact, since no impulse acts on a particle in this direction. As a result, MAVA1 is equal to MAVA2. Sorry, MAVAY1 is equal to MAVAY2, or VAY1 is equal to VAY2, since mass is constant. Momentum of particles B is conserved along the y-axis perpendicular to the line of impact, since no impulse acts on particle B in this direction as well. So consequently, VBY1 is equal to VBY2. Thank you. This is end of part C, and then the end of the lecture 5, principles of impulse and momentum. Thank you. Do not forget to like my videos, and then subscribe to my videos, to my channel, then share all the videos or the ones that are interested to you or interesting to you. Then always try to press notification bell for new videos if you have not done that. And then if you are one of my university undergraduate students, please do not forget to subscribe with your real name so that we can interact better. Thank you.